Hi guys, welcome to today's recording. I'm going to go through the 2021 NCEA Level 3 Organic Chemistry examination. So let's get started. So the first one, we are looking at the naming section in the drawing. So 2-methyl-pentanoic acid, start backwards. So start this way, butanoic acid, 1, 2, 3, 4, butanoic acid. 2 methyls, number 1, number 2, so put the carbons here and just make sure every single carbon have got 4 bonds. Okay, next one, so this functional group is a ketone. It's on the 1, 2, 3rd carbon out of 6 altogether, so this is hexane 3-on. And this one's 2-bromopentanoic chloride, so again work backwards, pentanoic chloride, 1, 2, 3, 4, 5. Acyl chloride COCl on the 3rd carbon, there's a bromine, so just make sure again every carbon should have 4 bonds. Now this is an ester COO, so this is a carboxylic acid side with 4, and this is the alcohol side, so this is methyl butanoate. Okay, all right, next one. C5H10O2. Oh, I love this type of question. So this requires you to actually understand quite a few things. All right, understanding the reactions, isomers, and just enantiomers, lots of different things. I love this type of question. So C5H10O. So every single one of these answers would have a molecular formula C5H10O. So draw the structure formula. All right, so a straight chain that will form bubbles when reacted with NO2CO3. So we know this must have a carboxylic acid. So this is the easiest one, C5, just 5 carbon. They say straight chain, so just like that. So you just need to understand that the function group must be a carboxylic acid. Next one, a branch chain. So with two different function group that cannot react with either permanganate or the carbonate. So it's not an alcohol, or primary or tertiary secondary alcohol at least, and not a carboxylic acid. Okay, so what are the potential candidate is that the 2 function group, and if you look at the formula, the 2 O's. Okay, so 2 O's, so it's not a primary secondary alcohol, so it could be a tertiary alcohol. So I can, make it look like this. So this is a tertiary alcohol. And then, so that's how many carbons do we need? We need 5. We got 1, 2, 3, 4. So we can put another one here. And it cannot react with either permanganate. So it cannot be a primary alcohol, cannot be an aldehyde. Okay, so we do have a double bond here. So the double bond O cannot go here, because if it went there, there'll be aldehyde. Aldehyde can be oxidized carboxylic acid. So the double bond O must go in the middle. Okay, so that's just a progress of elimination. You just need to know what we are dealing with, the potential outcomes, and just take trial and error. A branching alkane, a branching molecule that smells pleasant and can exist as an enantiomer. So it's pleasant means it's an C-double-bond-O, and it's a branch chain. So we could play around with. How do we? And we need to have a chiral carbon. So enantiomers means we have to have a chiral carbon. So you could start with a chiral carbon first if you want, to be honest. So we have to have an ester. So let's try and error. So I can do this. CH3, CH2, CH3. So this carbon right here in the middle, this one there, right there, is a chiral carbon because you're bonding to an H, O, and CH3, CH2, CH3, which are 4 different groups. So that's a chiral carbon. So that's 1, 2, 3, 4, 5 carbons already. So let's put an H here, and that should be the answer. Yep. Now a straight chain molecule that can decolorize bromine water, CC double bond, cannot exist as geometric isomers, so no cis and trans. So that means the 2 atoms, the 2 groups bonding to the carbon must be the same. You can react with the permanganate, but the resulting organic product would not form orange-red solid when heated with Benedict solution. So that means this reaction makes a ketone. It makes a ketone because ketone doesn't react with the Benedict solution, only aldehyde does. So how do we make a ketone? You must have a secondary alcohol. So we have we got a straight chain, so we've got 5 carbons. We must have the OH on the second carbon. Must have the OH on the second carbon, and it must have a isomer, geometric isomer. I can put it here. And double bond, and that will work. And I could also put the OH group maybe over here. That will work as well. Oops, there's no H there. CH2, CH3. Yeah, so this will work. I can move this OH group like here as well. I can move it here, it doesn't really matter. But this OH cannot be on the end because it has to be a secondary alcohol. So I can put the OH group here, I can put the OH group here, so either one's right. So I like this type of question. I feel this type of question, actually, you need to show understanding of what you're trying to do here. Not just, you know, that's like, if you look at this question, there's so many concepts. You got distinguishing tiers, function groups, enantiomers, and more distinguishing tiers. Very nice question. Next one, we're trying to, when heated with to form either pentanal or pentanoic acid, depending on the apparatus. So name the process carried out by each apparatus. So this is distillation, and this is what you use to make pentanal aldehyde, because it will stop the thing from further oxidizing. And this is reflux. This is one you use to make pentanoic acid. So why experiments to produce pentanal? So with distillation, what you want to do, so if you think about the products that we have here, right? So what we have, we've got pentan 1-ol. We've got pentan 1-ol will obviously react to become pentanal, which will obviously further oxidize to pentanoic acid. So by definition, well, not by definition, by just understanding the difference in the boiling point, these two that I just highlighted will have much higher boiling point compared to pentanal. The reason why is because they have hydrogen bonding and pentanal doesn't. Okay, so they have hydrogen bonding. So how distillation works is that if you set it up to a certain temperature, like just say if this boils at like say 50 degrees, this boils at 90, like 150 degrees, this boils at 120 degrees, for example. If you heat the thing at 100 degrees, then the pentanal, the moment that the pentan 1-ol react to become pentanal, they will be evaporated. They will, you know, they will fly up through the condenser, they come out the other end as liquid, and then you're not giving it a chance to further oxidize into pentanoic acid. Whereas reflux is that you crank up the heat. You don't care if it turns into pentanal or not, because you just want the pentan 1-ol to turn to pentanoic acid. Like, just make sure all of it react. So to maximize the rates of reaction, you heat it up as much as you can. And that's how it works. Okay, and then how it works is the condenser. So we can look at the answers here. So when we oxidizing it, distillation to make pentanal, because you are heating based and condensing based on the boiling point, because aldehyde low boiling point, so it's heated, it condenses back here. So with reflux, how it works is that you want to make sure it's fully oxidized. It produces pentanal, which vaporizes, and it goes up, and then it condenses back, and then it can be further oxidized. So it's just giving it a chance to react more fully, and then often, you know, sometimes the reflux reaction requires hours and hours and hours just to make sure everything have reacted. Okie dokie. Number 2. So what are we doing here? Use a chemical test to distinguish this propanoyl chloride. So straight away, when you see acid chloride, just add water. Okay, this is the easiest one. And by the way, propanamide is not basic. It's so weakly basic, which just says neutral. So don't go litmus paper. Only amines are alkaline. And don't think acid chloride is an acid. They only become acidic once they react with water. So if you put the propanoyl chloride in water, so what's going to happen here? If you put the propanoyl chloride in water, you are going to undergo a nucleophilic substitution. And then, because what's going to happen is that the Cl really wants to go, and the oxygen is like, hey, I'm rich in oxygen, electrons, let me come in. And then you have a substitution reaction. Okay, so nucleophilic substitution reaction. Very, very obvious reaction to do because of the white fume you're going to produce. Okay, so add water, the thing that reacts vigorously produces fumes. That is going to be your acid chloride. Now propanol and propan-2-ol, so can do a few things. With propanol, you can do right here tolins. You can do tolins reagent. You can do tolins. You can do Benedict's. Either one works. Tolins, you have a silver mirror, and then with the Benedict solution. Now this is very interesting. Remember going back up here, one of the questions is here. I'm just gonna highlight that for you. And this is purely just exam technique. Can you see? But the organic reaction product will not form red-orange solid with Benedict solution. So there you go. So what are you supposed to see when you have Benedict solution? If you put it in an aldehyde, you're going to see red-orange precipitate. Okay, red-orange solid, because they literally gave you the answers in the previous part. Okay, and so what it does with the propanol, you just have CCCOH, and then what it does, it just oxidizes into a carboxylic acid, whereas your propan-2-ol doesn't react. Now the reason for that, even though this is an oxidation, is that these two things that we decided to use, they are really, really weak oxidant, so they don't really want to oxidize. They don't want to reduce, but then the aldehyde are really, really strong reductant. They really want to reduce the other thing and then in turn oxidize. Okay, so there are the colors. You make propanoic acid, and then the color changes already there. Methyl ethanoate and propene. So this is alkene. When you see alkene, straight away bromine water. Orange or colorless, easiest one. Okay, and the other one doesn't react. So bromine water, you just break the double bond, add the BRs onto the carbons, and then very, very straightforward. You can also do potassium permanganate, using the oxidation reaction of the alkene to break the double bond, add two OHs, also works as well. Now let's have a look at this. Use the following amino acids. So this is what I was talking about before. I just recorded level 2 videos. It's level 3 organic. When we get to the polymerization section, it's going to be a lot of copying and pasting. So what you need to understand, so this one should be the easiest to do because they've drawn it they've drawn it for you. So what you just need to understand is that this is a condensation reaction. So what's going to happen? Is that this OH and this H, they're gonna go make water. So what's gonna happen? You see double bond O is gonna this carbon is gonna directly bond to this. Let me use different colors. Actually, let's go back here. Let's do this one on the. So this is what happens. So the thing on the left is the thing. The thing on the right is in blue. So once you understand that, the rest is just copy and paste. And why can you draw two possible structures? Is that you put the thing on the right. Now I'm gonna put it on the left hand side. See, I'm just doing that. And I'm going to put this thing over here. So this NH is gonna bond to this nitrogen. And then you can see it's only changing one thing. The rest is just copy and pasting. Very easy. Okay. All right. And that's a mirror equation. Wow. Really? Okay. All right. Now devise a scheme to convert propanone into ethyl propanoate. So you want to convert. So what are we starting with? We're starting with propanone. So we're starting with this. Excuse me. I'm just gonna be a bit late. Actually. Might as well. This is propanol. I want to turn it into ethyl propanoate, which is ethyl propanoate. Okay, so this is ethyl propanoate. So how do I get that? So you got a propanone here. Now you can't oxidize propanone. The only reaction that you learned in year 12 is that you can turn the propanone into a propan-2-ol. So you do a reduction reaction. And how do you do that? You use sodium borohydride and ABH4, which is a reduction reaction. And once you get to the secondary alcohol, so you need to see that over here, how do I, and then if you get stuck, it can work from both ways. Like, how do I make ethyl propanoate? So I need to use CH3CH2OH with acid and heat I need to combine this with, how do I make the propanoate? You need to use CH3 CH2COOH. So these are the two ingredients you need, and the acid and the heat, reflux to make ethyl propanoate. Okay, so obviously if you look at what we got so far, which is propan 2O, that's got nothing, you should be able to see it's got nothing to do with this ethan. This is ethanol. It's got nothing to do with that. So this is not part of the flowchart. All right, well, it's part of the flowchart, but it's not. We're trying to essentially turn this into this, but we can't, because this is propan 2O and this is propanoic acid. So this is a primary alcohol. So I just need to turn this into, so I can turn this, if I can somehow turn this secondary alcohol into a primary alcohol, because that's how we got ML4 minus H plus, because in order to make the propanoic acid, I need propan 1O. But I don't have propan 1O. I need to make, I have propan 2O. So what we could do is to reduce, to undergo elimination reaction to make the alkene. Got H here. To make the alkene, which is that. This is the alkene. And then you can turn the alkene to that by adding water and H2SO4, so diluted sulfuric acid. And this is going to be, so if you look at this, CH2, CH, CH3. When you add water, you break the double bond. You break the double bond, copy paste. So this is here 12. You add you can add the H here, you can add the OH here, you can add the OH here, you can add the H here, because this one has more hydrogen. So this is major, this is minor, this is one we want, so this is a minor product. So there you go, done. So you started with this. You can reduce that, because that's the only reaction from ketones. You reduce that to the alcohol, you reduce the alcohol to the alkene, then you do the major minor product to find propan 1O to propanoic acid to ethyl propanoate. Okay, so that's an excellent question. Question 3. So we got, so this is drawing enantiomer. So again, just highlight your chirocarbon. So it's going to be something like this. It does not matter how you draw it, as long as, especially the first one, it makes no difference how you want to draw the first one. Okay, so you just need to, you can pick and choose, you can draw it however you want. I'm just gonna go with this because I feel like it, I just draw it like that. So you just need to, the first one is, you can do it however you want, but the next one that you draw must be a mirror image of what you done on the left hand side. Okay, so this is no exception. So you have to be able to do this. So this one you can do whatever you want, but this one has to be a mirror image of the one that we draw. Okay, now how do we distinguish enantiomers? You shine polarized light through it. They will rotate the plane of polarized light in opposite directions. Okay, so based on the ability to rotate the plane of polarized lights, one goes clockwise, one goes anti-clockwise. All right, and this is another flowchart. Oh, they love flowchart in 2021. Okay, so this is question 3B, flowchart question. So this one right here, this is ethanoate. So heat under reflux, so that means we are breaking it. So let's have a look. Okay, they're not giving us a lot of clues here. So what are the two products? So we can just do it like this then. So if we heat it up, it's gonna do this, it's gonna do this. Okay, so one of them is gonna go in the box and one of them is going to the other box. So how do we know which one goes into which? We need to look at these reagents, look at the following reactions. So if we look at, this is a big hint here, tolerance reagent and heat. So that means this must be an aldehyde. And you can't, well, technically you can turn the alcohol into an aldehyde. You can also turn the carboxylic acid into aldehyde. But if you look at this side, conc H NH3. So this is possibly, if you look at the one that we have here, you can further react the haloalkane with conc NH3, but normally you need the alcohol condition. So I think what they're trying to do, this makes sense, is that they're asking you to figure out a way to turn the ethanol to the ethanoic acid, and they also want you to turn ethanoic acid into ethanoic acid. Okay, so this is a bit of a, I don't know, I don't agree with the logic here. So it just means I break it down. Oh, and by the way, this is something I always do. When you see CO double bond, always break it here, and that's how you can figure out what the two products are. So they're just asking you, all right, so I got these two things, how do I make both of them turn into the aldehyde? So we can try and error. Let's put this CH3CH2OH here, because this is the easiest one, because I turned the alcohol, I just turned that into a, if I just turn that into a aldehyde, that's done. And then I can just Toland's reagent, that's got to be that one. So what do we do here? So this is MnO4 minus / H plus. So this must be CH3COOH. So how do I turn it to something, turn it to this, turn it to back into CH3COOH? So let's think about that. All right, so this is CH3COOH. So all of these things must have a CO double bond somewhere. All right, so it's got to be all carb. They all have to have this. Okay, so this thing have to have that, which then did something with the conc NH3, which then did something with the into the carboxylic acid. So I'm taking a punt here because this is NH3, so this must be Cl. Because the reason for that is, like, you have to use carboxylic acid. I mean, think about all the functional group that you have in year 13 that has a carbonyl group. All right, so it's your ester, which is not that's the one we're looking for. Acyl chloride, this is the one that's going to turn into lots of things. Your amide, and then your carboxylic acid. So it can't be this. It can't be this. It can't be aldehydes or ketones. So it's got to be one of these. And it can't be amide. See, you can see the amide will fit in here, which is a nitrogen. So this must be the acyl chloride. So that means this must be the amide. And this must be another hydrolysis. So you're just going to cut it here and then replace it with the OH. So this is just acidic H plus / H2O. This is just acidic hydrolysis. So this is SOCl2. Okay, so quite a confusing question if you don't know what you're doing, but that's how I would break it down. Okay, so this is, you know, for an excellence question as well, not the easiest one to do. I'll give them that. Nice questions, to be honest, but it doesn't make sense if you already have something you want to go through all the trouble to make it again. It's not necessarily agreeing with that. Okay, all right, so this is polymerization, condensation, polymerization, and this was what I meant. Can you please, whenever you see COO bond, just draw a line between the CO single bond. Draw a line. All right, and then your life is going to be a lot easier, because can you see that that I draw the line, this thing and this thing are exactly the same, and then this thing and this thing is exactly the same. So you got your two monomers. So with the hydrolysis reaction is just, you know, you highlight one ester function. Oh, there you go, ester group. So hydrolysis is just adding water and you cleave it and then you break it down into the two smaller molecules. So the reagents required is with the acidic hydrolysis, you just add acid and water. With the basic hydrolysis, you just add base and water. Okay, so that seems a bit, you know, don't know why they want this, but you normally heat it. Okay, so for acidic hydrolysis, you want H plus / H2O, so diluted acid, heat, and then for basic hydrolysis, that means you need OH minus and water. So any strong base will do, like an AOH, chuck in water, and then you heat it up. Okay, so the structural formula of the two products. So this is where you need to So for the acid hydrolysis, it's very, now, doesn't matter what type of hydrolysis we're doing, guys. The first thing that you should always do is just figure out what the monomers are. And this is just copy and pasting. Like, you don't need to know what this ring in the middle does. And just copy what we identified as a thing that's being repeated. All right, so this is what we got. and let's just complete it. This is obviously OH, OH, and this is H and H because you added water, HOH, that's your water, H2O, all right? So this is what the two monomers are, but then the thing is that with acidic condition, can you see that this is a carboxylic acid? So in acidic condition, you're just gonna make these two. Okay, because they're not going to react with the they're not going to react with the acid. Acid doesn't react with acid. Acid doesn't react with acid. This is neutral. Neutral. They're not going to do anything. But if you do this in basic condition, what is it going to do? Is that your water, your alcohol doesn't do anything. But then what's going to happen is that the carboxylic acid that you made here is going to be further neutralized by the basic condition. So it's going to give you, and then this thing in the middle, COO minus. Okay, so it's just literally one letter and one symbol difference, but that goes up to excess. Okay, so here you go. So hydrolysis reaction is just breaking down a large molecule into small molecules. You gain water, gain OH, gain H, and then both are happy. And then you require heat, and then one use acid, one use base with water, and then you break them down just like the one that we did. Okay, so hopefully this makes sense. I think this is the exam. Yeah, very short exam to be honest. But some of the distinguishing tests and some of the not the distinguishing tests, the flowchart can be a little bit tricky there. Okay, so hopefully this is helpful, and leave a like and subscribe if you haven't. Share it with other people that are struggling in chem, and I'll see you guys next time. Bye bye.